Hello everyone! The point of this video is to explain how a chain of 5 iron atoms on copper nitride, that each behave as a spin-2 system, can be put close to a so-called diabolic point, and how this enhances its spin lifetime. So, let's bring our 5 atoms into action. Here they are. Now let's make some room for the Hamiltonian. We'll build up the entire Hamiltonian in parts. First, let's turn on the uniaxial magnetic anisotropy, which is a result of how the atoms lie in the copper nitride lattice. With D being negative, this makes the ground state ms equals 2. Or actually, it can be plus 2 or minus 2. The arrows here indicate that the spin's z-axis is along the axis of the chain. Now, if we apply a small magnetic field along this axis, say 100 millitesla, we'll select one of these two states as the ground state. This is due to Zeeman splitting. Next, we're going to couple these atoms together using a term J, which we will pick to be positive. That way the coupling is antiferromagnetic, so that the neighboring spins are opposites. This coupling is due to the relative position of how the atoms lie in the copper nitride lattice. Now, the two lowest energy eigenstates, psi0 and psi1, are very close in energy, less than 1 millielectron volt apart. Psi0, the ground state, is as shown. And psi1 is the opposite. Let's call these states Na and Nb for so-called Néel states A and B. Okay, so far so good? Now we're going to introduce the final term of the Hamiltonian, the transverse magnetic anisotropy. This is also a result of how the atoms lie in the copper nitride lattice. This term essentially mixes the states. In other words, psi0 and psi1 now become superpositions of Na and Nb. They still have a majority contribution in their original Néel state, but now they also have a minority contribution in the opposite Néel state. Notice that psi0 is a symmetric superposition, as there is a plus between the two. And psi1 is an anti-symmetric superposition because of the minus between the two. There's still an energy difference between psi0 and psi1, but this time it's not only because of Zeeman energy, but also, in fact, because of the symmetry and anti-symmetry of these two states. Now, on a different note, because of this superposition, it's also possible for this chain of atoms to randomly switch between these two states. And if we want to use this chain for qubits or spintronics or something like that, we generally don't want it to randomly switch. So we kind of want to be able to suppress this superposition effect so that it remains stable. But how could we do that? Well, let's plot the energy of the two states when adding a term Bx, so a magnetic field perpendicular to the chain. It'll start off big, due to the symmetry effect, but then it becomes smaller and smaller until at some point it almost crosses. It's an avoided crossing between psi0 and psi1, with the energy difference being the Zeeman energy. Now we're going to take a look at the majority contribution of psi0 and the minority contribution of psi0, and we'll show it in this tracker on the top. Okay, we start in a symmetric plus-plus situation. As we increase Bx, state would like to continue on this dotted path, to continue being symmetric. But it cannot. Instead, it'll take over the anti-symmetric state coming from psi1. Now, we're in the anti-symmetric situation, minus plus. But wait, the minority started positive, now it's negative. So then exactly at the avoided crossing, yeah, it'll be 0. And so psi0 is fully Nb. And the same thing applies to psi1. It starts anti-symmetric with a minority positive, turns towards symmetric with the minority negative, and right in the middle, the minority goes to 0, and so psi1 is fully Na. Now in case you missed it, let me show it one more time, this time with a block sphere. Here we have psi0 fully Nb, psi1 fully Na. And at this point, psi0 turns symmetric, and psi1 turns anti-symmetric. And after this avoided crossing, psi0 is anti-symmetric, while psi1 is symmetric. I'm back at the avoided crossing near in between, fully Nb and fully Na. So, did we do it? Did we remove the superposition? Well, kind of. In practice, it's not entirely gone because of some other details. But still, if we were to plot the lifetime of the state as a function of px, we do get a peak right at this avoided crossing. And this lifetime is something we can very easily measure with great resolution. Now, the keen observer might realize that I promised a so-called diabolic point. So, is this avoided crossing the diabolic point? Almost. For that, we need to also show the energy as a function of Bz. So we get these energy planes. When Bz goes to 0 and there's no Z1 energy, and we pick the Bx such that there's also no symmetry energy, the energy difference between psi 0 and psi 1 goes to 0. That's when we get the diabolic point, which is right there. Now, if you look closely, you'll see an almost linear increase of the energy difference between psi 0 and psi 1 with increasing Bz. That's the Zeeman splitting. So why do we need the Zeeman splitting? Well, it turns out that this actually helps us to make the peak in the lifetime not being infinitely sharp. So it actually has some width, so we can actually measure it. And measure it we did. Now, for further results and further details, please refer to the links in the description. Thank you for your attention.